me know. Oh, no, no, record. Okay, stop. Okay, so let's start. So today's topic is on mean and variance of random variables. Yes. So we talked about what random variable was last time before our test. So what exactly is random variable? Any ideas, or you guys totally forgot, or what idea do you have about random variable so far? What is random variable? What do you understand by it? How is it related to probability? Just go for it. If it's wrong, it's okay. Come on, guys. You want me to have definitions in the test exam? Okay, so let's go back to our previous lecture since everyone doesn't know what random variable is. Let's see, module number. Again? What was it? I don't think you finished the sentence. Okay, so tak apa, it's okay. So let's go back because I know everyone had a really good break and forgot everything already. So we know that we have two types of random variables, discrete sample space and also continuous sample space. Now what is that? Go over your notes again. And who's texting me? So this is the graph for discrete random variable. Discrete probability distribution for random variable. And random variable basically assigns a number to the probability. It assigns a number to the probability. Sometimes if we don't have random variable, we could just say, oh, this thing is 0.21, that thing is 0.31. But instead of saying that thing, this thing, we say, okay, what if we define a random variable as the number of flaws that we see on a paper, for example. So if I see one flaw on the paper, I would say the random variable x is equal to 1. If I see two flaws on the paper that I'm taking, then I would say that the random variable x is equal to 2. So basically what we're saying is we eliminate all those sentences. Instead of saying there are two flaws on this paper and the probability is blah, 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 we just say, okay, the random variable x is equal to 2. And I immediately know that it's referring to the number of flaws that I'm observing on the paper. For example, we've gone over a lot of examples before. You can go over those again. Basically, what random variable is just assigning a number to a probability. So that is your random variable. So that's the concept here. So we're going to continue with that on module 6. Sorry, this is module 5. Module 6. Am I screen sharing? Can you see? Okay, yes, you can see, supposedly. Okay, so that was what random variable was. We talked about discrete random variable and also continuous random variable. And we saw two different types of graph where for discrete, we saw that it was lines, and for continuous, we saw that it was a curve, right? And we also talked about marginal, probability density. You guys still remember that? Joint probability distribution, probability mass distribution. Those were, but there were a lot of terms and you have to remember for it to make sense in this lecture. Okay, so let's continue. So the mean, we know what mean is. We talked about this in the first lecture. The mean is basically the measure of the center or the middle of a probability distribution. So if I had a bunch of numbers, 1, 5, 6, 7, 8, 9, and I know that 1, 2, 3, 4, 5, 6, I have 6 numbers here. I add them all together and I divide it by the number n, or 6 in this case, I would get the mean. Previously, we denoted mean as x with like the hat, right? But now we're talking about, to switch off my WhatsApp. Okay, now we're talking about mean of discrete random variable, which is going to be different. So it still means the measure of the center or the middle. Sorry, previously we talked about x as the average. It's not the middle. The middle was median. Remember, median was the middle of the sample space. For example, you have 1, 5, 6, 7, 8, 9. The median would be the middle of these numbers, which is 6 and 7. So you had to plus these two guys together and divide it by 2 to get your median. So median tells you what is the middle value for your sample space, and mean tells you the average. But for mean of discrete random variables, it tells you the middle of the probability distribution. So for example, if I'm going to show you the graph of discrete random variable that we saw earlier, let me try my best to draw it nicely. Okay. So, oh, this is so bad, but never mind. Okay, let me try again. So this is our x random variable, and this is going to be my probability. Okay, and my random variable is 0, 1, 2, 3. Let's say 0, 1, 2, and 3. And whatever line that I put in will represent the probability for each random variable. For example, for x equals to 0, the probability is 0.2, and for number 1, probability is 0.3 maybe, who knows, and whatever that is. And the total probability, provided that this is a complete set, the total probability should be equal to 1 total. Okay, so what does the mean tell us when it is about random variable? So if I were to calculate the mean, it would tell me the position. For example, if I get the mean as 1.5, oh, this crayon is bad. If I get the mean as 1.5, then I would say, okay, so the middle of the probability distribution is at 1.5. It is between here, between 1 and 2, and it is where the probability distribution is at balance. This is what it means. Okay, so what is the equation for that? Let x be the discrete random variable with probability mass function. So px is for discrete and fx is for continuous, but it can be anything really. It can be f, it can be g, but for clarity for this class, we're just going to call it p for now. So px is probability of x equals to some value of random variable x. The mean of x, random variable x, is given by mu subscript x equals to the summation of all the values of x times the probability of x. So that was a mouthful, where the sum is over all possible values of x. So when we have this sum symbol and it has x over here, it means that you are going to add all the values of x. The mean of x is sometimes called expectation. So sometimes they label it as this guy. So if you see this, don't panic. It simply means it simply means the mean, or mu x. Okay, it's the same thing. Mean of random variable x. Okay, RVX. Let's just call it that. So the mean of x is sometimes called expectation. E is expectation or expected value of x, and may also be denoted as EX or by mu. Okay, so again, we saw mean as this symbol previously. That was for sample or for population. For random variable, the mean is denoted by mu. So don't get that confused. The equation is also different and they also mean differently. It's almost like median, right? Okay. So example. So any questions before I move on to the example? Everyone okay with the definition so far?
Yeah, so far okay.
Okay, thank you. I just spilled my coffee. Okay, so read that example first. I'm going to talk about it. Okay, so a certain industrial process is brought down for recalibration whenever the quality of the items produced fall below specification. Okay. Okay, let X represent the number of times the process is recalibrated during a week and assume that X has the following probability mass function. Okay, so when we have a probability mass function, we know that the total probability should be equal to 1. Probability mass function is always a complete set of probability function. Okay. So find the mean of X. So X is a random variable. How do we know it's a random variable? Because it says here, let X represent the number of times the process is recalibrated during a week. So it is assigning a number to an event, or like to an event. And assume that X has the following probability mass function. And for each of the random variable, there is a probability, there is a value of probability, and therefore we have the probability mass function. So now we have to find the mean of X. So let's go over the definition again. So let's try to do this. So mu of X, or the mean of random variable X, is the summation of X, random variable X, times with the probability, and you add that all together, add all of those together. So X, mu of X is equal to the sum of all the values of X and times with the probability of this guy. So how does this expand? So first you go with 0. This is the value of your random variable. And then what is the probability for that random variable? It is 0.35. And you have to add all of those together. So 1 times 0.25. I think it's fairly straightforward, but you have to know what the equation is telling you. 2. Oh, this is a really bad 2. 0.2 and 3, 0.15 and 4, 0.05. Okay, so are we missing anything? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if we add all of those together, I think it's around 1.3 something. Let me get my calculator. Okay, so 0, you don't have to calculate for that. 0.25, 0.4, 0.45, and 0.2. You would get 1.3. Okay, so the mean of random variable X is 1.3. So what does that mean? Let's see. This is the solution. So this is our graph for the probability mass function. And again, this is where our mean is. And this is where, how do I say this? There's a balance. I don't know how to say, how do I explain this? It is the point where the probability is at balance. So let's take that definition and bear with me as I continue to explain about this. Okay, so now that we talked about mean, of course, there's going to come the variance and standard deviation and all those stuff. So now we're going to talk about population variance of discrete random variable. So again, let X be the discrete random variable with probability mass function. With probability mass function Px, probability mass function equals to probability of random variable x equals to some value of x, then the variance of x is given by, so it's the same symbol this time. So we don't have to worry too much about that. Same symbol, it is equal to the summation of x minus the mean of x. Sorry, this is random variable x minus the mean of random variable x squared times with the probability. Doesn't seem too bad, right? And an alternate formula for the variance is given as summation of random variable x squared times with the probability minus the mean of random variable x squared. So sometimes it's easier to use this one, sometimes it's easier to use this one. I think the second one is easier, but let's see which one is better for us to use in solving problems. Okay, so what does population variance tell us about our random variable? So recall that for a sample x1, x2, x3 up to xn, the sample variance is given by the x minus with the mean squared over n minus 1. We talked about this in the first or the second lecture early on in the course, because we talked about this and then we talked about variance, right? So recall that for sample variance, this is the equation whereby your sample value is minus with the mean divided by the total number of sample minus 1. This was for sample variance. For population variance, it was divided by n. That was the difference. The sample variance is thus essentially the average of the squared differences. The average of the squared differences. You have your sample, you minus it with the mean, so this is the difference. You square it and you divide it with the number of samples, therefore it becomes the average, right? The average of the squared differences between the sample points and the sample mean. So that was the definition before. On the other hand, the population variance of a discrete random variable x is the weighted average of the squared difference. Now there is a similarity somewhat between the sample variance that we talked about earlier on and to the population variance of a random variable, in a sense that you have to minus with the mean. This is your random variable, minus with the mean, and you square it. This guy, you have your sample, minus with the mean, and you square it. But instead of dividing it by the number of samples, you don't do that. You just multiply it with the probability. So because you multiply it with the probability, it becomes weighted. It's not average, it's weighted. Remember, probability is gives us the weightage of your sample. For example, what does weight mean? Okay, I have this sample 1, 1, 2, 2, 3, 3, 4, 4. I hope I don't screw up on this example. 5, 5, 6, 6, 6, 7, 7, 7, 8, 8, 8, 8, 8. Now I can say that for the number of 8 occurrence, the number of 8 occurring is the most weighted, because it occurs the most in this sample space. It occurs the most. Therefore, it has the highest weight. But if we translate it in terms of probability, I have to do some calculation, which I don't want to. So how do I say this? We know that probability distribution tells us how often something occurs, right? It means the same thing for weightage. So the higher your probability distribution, the higher the weightage. So this is why they say population variance is the weighted average, because you multiply it with the probability. You are telling how often it occurs. Okay, is a weighted average of the squared differences. Hopefully that makes sense. I know statistics is like a lot of equations, and I hope at least we get some concept down. Okay, so if you have any questions, you can ask me. So the variance is a measure of dispersion. So we talked about the mean. The mean tells us the balance in the probability distribution. But for the variance, it tells us how dispersed the sample is, how dispersed, how it varies, how it spreads out. So this is what it tells us. Why do we need to calculate the variance? Because the mean or expected value of random variable X describes where the probability is centered. And that's great. Sometimes we need to know it. However, the mean does not give us adequate description of the shape of the graph or the distribution. This is where the characterized of variability in the distribution is introduced. So this is why we need variance, because I'll tell you in a bit. Figure below shows example of two distributions. So this is the first distribution and this is the second distribution. Both of these graphs have the same mean. You can see that they have indicated with a dotted line, or sorry, a dashed line. So the mean is at number 2. How do I write mean? Mu. Mu of A, let's say this is A and this is B. Mu of A is 2. Mu of B is also 2. But even though the mean is the same, the shape is different. So how do we distinguish between two types of data? So this is where your variance come in. Your variance for this guy will be obviously different than B, because this one is more spread out. This is a very bad handwriting, whereas this one is less spread out. So, okay, can anyone tell me, is a widely spread out data better than a less spread out data? Which one is better, A or B? Which one is better? Which is more accurate?
B.
B is more accurate. Why? Do you have any justification? It's okay if you get it wrong or right. I don't mind. We're just having a discussion.
It's A.
Someone said it's A. Okay, why A and or why B?
Because the value deviate less compared to B.
Again, because it is less
The value deviate less compared to B.
Okay, because A deviates less compared to B, correct. When we talk about variance, the smaller the variance, the better the data actually, because it tells us that the data is close to our approximation. Because when we have a bunch of data, we have a large number of data, and we approximate the mean, we approximate the median and whatnot. The variance tells us the shape of the data, how distributed it is. And if it is widely distributed, it means that it is going to be far away from our approximation. Versus for this guy, it is closer to the mean, right? And this is further away from the mean. So a higher variance indicate that the data is less reliable, whereas a smaller variance tell us that the data is more reliable. Not to say that the data is wrong, it's just less reliable or less accurate. And if we had the choice, we would go for something that is more reliable, but sometimes we don't have that choice. So it depends. So the variance tells us what type of data that we have. So this is why we need to know what is population variance. Okay, thank you for that. Good answer. Okay, moving on to an example. Find the variance and standard deviation. We talked about the equation already, right? Okay, find the variance and standard deviation of the random variable X. So this is our probability mass function. It is the same as before. 0, yeah, it's the same as the previous example. I'm just reusing it. So now we want to know what is the variance and standard deviation. So let's look at the equation again. Okay, so our equation is this. How do we use it? So sum of random variable minus the mean of the random variable squared times the probability. Which one should we use? Let's use the first one. X minus mean, okay. The symbol is this guy, squared. If it doesn't have any squared, it means it is the standard deviation. Now we're talking about variance. Okay, so the sum of X minus mean of random variable X squared P probability of random variable X. Okay, so let's do this. We know what the mean is from our previous calculation. It was 1.3, right? Okay, let's reuse it because it is the same data. Don't want to do the same thing over and over again. So X is 0 minus 1.3 squared times with the probability of that for this guy times 0.35. That's the number 3. Looks like a squid. Plus with 1 minus 1.3 squared and 0.25. I'm going pretty slow here. 2 minus 1.3, 0.2. Sorry, I'm missing the square. Plus with 3 minus 1.3. And you get the idea, I think. Squared 0.15 plus 4, 0.1.3 squared 0.05. Okay, so hopefully this is the right way of writing it. Let's see the solution. So 0 minus 1.3 squared, blah, 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 same thing as I did before. And the answer is 1.51. Okay, so random variable X minus with the mean, square it, times with the probability, And from your variance, you can also calculate the standard deviation, which is just the positive square root. Do not give me negative standard deviation. Please give me only positive values. Okay. So for that, the variance is 1.51 and the standard deviation is 1.23. So what if we wanted to use the second equation or the alternate equation? Let's see. So the alternate equation is x squared times with the probability minus with the mean squared. So let's do that. Is it going to be easier or is it going to be harder? Okay. So this is, I need a pen that is a different color. So, so sum of x squared times probability minus mean times with the probability minus the mean of x squared. Is it squared? Yes, this is squared. So you have two squares here. For the previous, you only had one. Okay. All right. So let's try. So 0 squared times with the probability 0.35 minus with mean squared 1.3 squared. Okay. Plus with 1 squared. Probability is 0.25 minus 1.3 squared. So can we simplify this equation in any way? Is it possible? Plus with 2 squared, 0.2 minus 1.3 squared. Okay, so I think you get the idea on how to expand the equation. So here actually you can add these all first and then minus it with 1.3 squared. But you have to have this. Okay. So it's the same actually. How do I say? Let's see. Is this not part of the sum? Then they should have indicated it like this. Okay, so let me put this bracket over here first. I need to double check on this. For now, let's assume that we add these all together first and then minus it with the mean. If we minus the mean one by one, I think it will give a different answer. So let's follow the solution first and I'll try to clarify with the coming examples. Okay. So that was the alternate solution. It was easier, but it also invited confusion. So both works, it will give you the same answer. Okay, so if you get confused, you can use the other equation and just compare. If you have the time, if you don't have the time, then don't do it. Okay, so now we're going to talk about the mean and variance of continuous random variable. Let X be a continuous random variable with probability density function fx, then the mean of X is given by. So it's basically the same equation except that now you have this integration sign. The mean of X is sometimes called the expectation or expected value of X and may also be denoted as EX or by mu. Same definition, everything is the same except that now we need to integrate. So for this guy, this is the variance. We talked about the mean and also the variance. Same case for the continuous random variable. Same equation as well. We also have an alternate equation. And I'm assuming that this does not include mu x as well. Let's see for the, oops, sorry, not this one. Okay, so this is the equation for variance, same thing, except that we have integration. The variance of X may also be denoted as Vx. And we have for this guy, Ex, mean variance. For standard deviation, there's no short form, there's no letter assigned. Just use this to indicate standard deviation and this to indicate variance. Okay. Okay, so let's do an example. The probability density function of random variable X is given. Find the mean and variance. So this is a continuous probability density function. We need to find the mean. So the equation for the mean is mu x, x fx dx. Okay. Mu x integrate minus infinity to infinity x fx dx. Okay, fx dx. After this topic, let's take a break for 7 minutes. Okay, so let's focus for this one first, and then we're going to take our break. So mean of X for a continuous random variable X is given by X fx. Previously, it was X px, right? But for continuous, it's fx. But it's actually the same. You shouldn't let the letter confuse you because they can change the letter anytime. They can tell you X, JX. What equation is this? So the letter is just there to help you, to guide you. It can be any letter actually. Okay, so how do we do this? It goes from 0 to 1 and it is 0. Otherwise, find the mean and the variance. So let's just plug in the equation. So first we start with minus infinity to infinity, but X only goes from 0 to 1. So this is our boundary. And we have our random variable X, and we need to plug in our function fx. So our function fx is 1.25 times 1 minus x to the 4 and dx. We integrate it with respect to x. 1.25 is a constant. You can put it outside of the integration, or you can just leave it there. I'm going to put it outside. So this is 0, 1. And x times with 1, x times with x to the 4. So you would get x minus x to the 5 dx. I'm just expanding. I'm not doing anything yet. Now I'm integrating. So x squared over 2. I don't have space. Let's do it over here. This is fairly easy integration. I think the tricky part for our course is actually applying the equation. So hopefully everyone has gotten down their integration because I cannot teach that one here. It's too much content. Okay. All right, so now let's try to integrate x squared over 2 minus with x6 over 6. And I have my constant 1.25, and this we need to put in the value 0 and 1. So whatever that is going to be our mean. So let's see the solution. X squared. Where did the x squared come? Oh, sorry, this is the mean. I got confused. This is the variance. So the mean is x 1.25, 1 minus x to the 4. I think this is the same thing that I did earlier. And you just plug in the values and you would get the mean. And for the variance, the equation, let's go back to the equation over here. The mean is x fx. The variance is x minus mu x squared. But for the solution, they use this equation, the alternate solution, the alternate formula, which is x squared fx dx minus mu squared. So here you have this dx over here. So it indicates that the integration only goes up to this part. It ends here. Okay, so I'm just going to put that bracket over here. This guy, you don't integrate. You only integrate up to this part only. Okay, so this is the solution, x squared fx dx minus, we already know what the mean is from here. I think this is fairly straightforward, x squared times with the function fx from here. Okay, and then you multiply the same case as over here. You just multiply it, expand it first. If it confuses you, expand it first, and then you integrate. Then you plug in the values. Okay, so this is how you use the equation. Okay, let's take our 7-minute break. Let's come back at 9:50. If you have any questions, you can ask them now, personally if you want, or to the class as well, you can. So let's come back at 9:50. Have a great break, and I'll see you back at 9:50. Any questions? No questions? Oh, Selamat Hari Raya to everyone. Forgot to mention. Petang ni ada amal ni.
Jangan
Is the internet bad at the hostel? Because I think you guys are not finishing sentences. Or is it my internet? I don't know. Okay, welcome back everyone. Let's continue. Oh, I'm still recording, right? Yes, okay. So we talked about mean of, what was it? We talked about the mean and the variance for random variable, continuous random variable, and it was slightly different than the discrete one. The equation was the same, but the difference was the integration part. So I don't think the equation is too bad if you need to remember it. It's the same thing except for the integration versus the summation part. One thing to note is, there's an alternate equation. The alternate equation, you have to take note that when you have this minus mean, consider everything else in a bracket. Same case for the discrete. This part is not part of the summation. That was my mistake. So this, you need to keep in mind that the squared x times with the probability, you sum it all up and then only you minus it with the squared mean. Okay, so I hope that's clear. Okay, let's go back to our content. Okay, so now we're going to talk about means of functions of random variables. We have not talked about functions of random variables before, so this is new. What is function of random variable? For example, I have a random variable x, we know this. And I say, okay, I want to define a function, and this function is a function of x. For example, I have, let's say hx, they use hx here. So hx, let's say it is ax plus with b, example. And this is a function, it's a legit function, and this function is a function of the random variable x. I should write it as like this. Okay, so we know that this function is dependent on random variable x. Therefore, hx is a function of random variable x. It's just a normal function actually. Okay, so now that we know that hx is a function of random variable, how do we find the mean for this function? So this is what this slide is about. So let x be a random variable and let hx be a function of x. Okay, then if x is discrete with probability mass function of px, the mean of hx is given by mu, they indicate it like this. Previously it was mu x like that. But now we're talking about the mean of the hx. Therefore, it's mu hx, summation of hx px, where the sum is taken over all the possible values of x. Now, how is this different compared to the mean before? So previously, we talked about mu x, summation over all the values of x, p, x equals to x, which is the same, except now your x is hx and this guy is hx. So it's almost the same. You just have to like add the function in. So the function is not going to be x. It's going to be something more elaborate. For example, pi x over 4 or 2x squared plus 3. So it can be something like that. As long as there is an x in the function, it will be hx. So you need to plug in to this equation. So let's see how we can use this equation to solve our misery. There's a lot of equations where the sum is taken. Okay, for if x is continuous with probability density function fx, the mean of hx is given by, same case over here, except that now we have to integrate. This is for continuous and this is for discrete. Why do I have the same slide over here? Okay, never mind. Example, an internal combustion engine contains several cylinders bored into the engine block. Let x represent the bore diameter of a cylinder in millimeters. I don't, for this lecture, I don't think the question really matters because we're talking about the equations a lot more. But for when you're talking about conditional probability, when you're trying to find whatever that we covered for the test, that was when the question was really important. But for this lecture, we're just concerned about what is the probability mass function? How do we use the equation? So this is the focus for this lecture. Okay, so let X represent, if you're scared of the question, don't be, just look at the equation. Let X represent the bore diameter of a cylinder in millimeters. Assume that the probability density function of X is given as this guy. So this is continuous. Let A equals to pi x squared over 4 represent the area of the bore. So A is our hx, or it's a function of the random variable x. Find the mean of A. So just the equation, first of all, the equation is mu hx integration. It was hx times with px, right? hx times with px. Sorry, it's fx because it is continuous. For our probability density function for discrete, it was hx px. And it was the summation over x. Okay, so here, this is the equation. So what did they do for this guy over here? They wrote it as mu of A, because A is our hx, or the function of the variable. And same case over here, infinity, minus infinity to infinity. And our hx is this guy. So we put into our equation 4. And our fx is given by 10. It is possible. So our fx is just 10. And we integrate it over all the values of x. So now, instead of minus infinity over to infinity, we know our x only goes from this value to this value. So we can rewrite this and put it as 80.5, the lower one at the bottom and the higher one at the top. So this is how you write the equation, and you solve it as usual. Your 10 is now a constant, so it's quite easy from this. So pi x to the 3 divided by 3 times 4, and then you times it with 10, and then you just plug in the values. You would get this number. Okay, any questions so far?
No question, Doctor.
Everyone's okay? Does anyone want me to repeat any part? Okay, Ken. Okay, so I'm going to continue. If you want me to repeat, please let me know.
Hey,
Yes? I heard someone say hey. No heys? So you are retracting the hey. Okay, so let's continue. Okay. Now we're going to talk about the joint. What if we have a joint distribution? Where's the equation for that? I think this example should come afterwards. Okay. So now we're going to talk about the mean of jointly distributed random variables. Okay, so previously we were talking about the mean of function of random variable x. Jointly distributed, we already saw this earlier. And when we talked about jointly distributed random variables, we were talking about marginal probability distribution of x, marginal probability distribution of y, and it was on your exam. So I think you still remember that. If x and y are jointly distributed random variables and hxy is a function of x and y, sorry, I did these slides at 5 a.m. So there's bound to be mistakes, is a function of x and y, then the mean of hxy can be computed from the joint probability mass function or joint probability density function of x and y. Okay, so let's look at the equation. If x and y are jointly distributed random variables, such as hxy is a function of x and y, then x and y are jointly discrete with joint probability distribution joint probability mass function Pxy. This is for discrete. So mu of Hxy, whereby Hxy is a function of x and y, random variable, you have to sum over the values of x and you have to sum over the value of y. Same case like before. And now we have two functions. Instead of just Pxy, which we saw earlier, we have another function, which is the Hxy. Okay, let me try to recall for you. Previously, it was, we were talking about the marginal probability distribution, and it was Pxxy, I think. And you had to, this was the equation. So this is marginal distribution probability, marginal probability distribution. This guy is the mean. It looks the same, but it's not. So you have this addition over here, and you also have to have the both x and y, the summation of x and y, where the sum is taken over all the possible values of x and y. If x and y are jointly continuous with joint probability density function of fxy, then the same case over here, we have the same equation, except that now it's integration. And again, this is generalized. You would be given the boundaries for your x and y. So you have to replace your minus infinity and infinity. Okay, don't use infinity and minus infinity unless the function is like that. Okay, example, let x represent the diameter of the cylinder ball. Let's not read the question. The displacement is given by d. This is our function. So d is pi x squared y over 4. So our function here is a function of two random variables. We can say it is a hxy, which is what we were talking about earlier. Assume x and y are jointly distributed with joint probability mass function given. So this is our joint probability mass function. And it has two boundaries, one for x and one for y. And otherwise, if it's not between these values, it is going to be a 0. So just plugging in the equation, I think it's fairly simple. Hx times with fx. We know what our hxy is. Sorry, this is a joint probability distribution. Hxy and fxy. So what is our hxy? It is pi x squared y over 4. What is our fxy? It is 100. Only if your boundaries cater to this. So you have to change the boundaries. So for your x, you have to go between 80.5 to 80.6. And for your y, you have to go from 65.1 and 65.2. So the rest is just normal integration. It looks quite simple, right? Except that it's joint. So just keep that in mind. You have two integration to do compared to the previous one, which was only one. And of course, we have variance if we have mean for jointly distributed probability mass function. This is it. Expected. Let's just focus on this one. So is x minus the mean of x. It is the product of x minus the mean of x with y minus the mean of y times with the probability mass function. And if x and y are discrete, this is covariance. This is not it. This is covariance. This is it. What are we looking at here? The variance of the random variable gx is gx. This is not joint. Okay, never mind for this one. We are not touching covariance yet. Kejap lagi. We're going to look at it in a bit. First, we need to go over the definition. Okay, so any questions about jointly distributed probability mass function where the function is a function of random variable X and Y. Any questions about that one? I think it's fairly straightforward, right? Just remembering the equation is the tough job here, is the toughest part. It's a lot. No questions? Okay, I'm going to continue. So now that we talked about mean, we talked about variance, we talked about its relation to random variables, and we talked about the function of random variable. We also talked about jointly distributed random variables. We also talked about the mean and variance for discrete and continuous, right? So now comes, I would say, the last part for this lecture, which is covariance. What is covariance? First of all, it has the word variance in it, which tells us the spreadability of the data. But we have this word co, which means that they have like some sort of collaboration. I would like to think that way. So covariance is the relationship between two variables or two random variables. When two random variables are not independent, they have some relation with each other. It is useful to have a measure of the strength of the relationship between them. And covariance tells us this. The population covariance is a measure of a certain type of relationship known as a linear relationship. So covariance is a linear relationship. It's not squared. It's not it's not squared or like to the power of 3 or anything like that. It's a linear function. We will usually drop the term population and refer simply to covariance. Whenever I say covariance, I am actually indicating population covariance. Okay. And also for the mean that we talked about earlier, it is for the population mean, but we just say mean. Okay. So what does covariance tell us? It follows that if cov or covariance is strongly positive, then values of xy in the first and third quadrants will be observed much more often than the values in the second and fourth quadrants. Okay, I want everyone to focus on this one because graphs is a popular question. Okay, popular question, hint. Okay, so it says here, it follows if it is strongly positive, if your covariance value is strongly positive, we don't know how to calculate covariance yet, but I'm just telling you, if covariance is positive, then the values of x and y in the first and third quadrant, I don't want to say x, in the first and third quadrant, the first and third quadrant will be observed much more than the values in the second and fourth quadrants. Okay, so let's see if that is correct. So A indicates a random sample of points from a population with positive covariance. So this is our data. It is spread out, but it is more spread out in the first and also in the third. So why is it spread out in the first and the third if your covariance is positive? So let's see. So here they indicate to us that, let me just try to zoom this. It indicates to us that over here, the product of these two product of deviation between x and y is positive here because, okay, first I need to describe the graph. Okay, so this graph has axis x as mu x and the y-axis as mu y. So over here, it is positive. Over here, it is negative. Over here, it is positive. Over here, it is negative. Everyone following me so far?
Yes, sir.
Yes, okay. So just bear with me first. So mu x and mu y, when they intersect, they indicate the origin. When they intersect, they indicate the origin. That is why beyond here, it is positive, and over here, it is negative. Same case like we saw in our regular graphs. If this is our origin, this side is going to be positive. This side is going to be positive. This side is going to be negative. This side is going to be negative. Here, our origin is the intersect between the mu of x and also the mu of y, which is the mean. It's not a random It's not a random value, it's the mean. We have to calculate for it. So the intersect between the mean is our origin. So anything beyond the mean is going to be positive. Anything that is less than the mean is going to be negative. Okay. So now, if we know that going up and going to the right is positive, so positive with positive will tell me that this value over here is positive. Positive with positive. Negative with negative also gives me a positive. A positive with a negative gives me a negative, and a positive with a negative gives me a negative. So that is why when your covariance value is positive, your value will be much more distributed in the first and the third. It's not going to simply mean that you won't have any data in the 4 and 2 quadrant, but it's saying that you would have more in the first and the third. So your data is spread out, and this is how you interpret it. Okay. So this is B. B is more spread out in the second quadrant and also in the fourth quadrant. And remember, this side over here is positive. This side over here is, sorry. So this is positive, negative, positive, negative. Therefore, this is going to be positive, and this is positive, this is negative, and this is negative. So if my data is spread out more in the second and the fourth, therefore my covariance, I can already say, oh, my covariance is going to be negative. Or if they give you a negative covariance, you already know that your data is going to be spread out more in the second and fourth, vice versa. Okay, what about C, the graph in C? So you can see that this guy does not have any bias. It's not biased to the 1, 2, or 3, or 4. It's close to the mean, almost close to the mean. And you would say that the covariance for this type of data is close to 0. Close to 0, not equal to 0. If they were 0, they would be like exactly on the line itself, but it's not. So it's near 0. It's close to the mean, but not there yet. Okay, so everyone okay with the graph interpretation so far? If I ask you a question on test, would you be able to interpret the graph? So everyone doesn't want to answer me on that one. Okay, fair game. So in a random sample of points, therefore larger values of X would tend to be paired with larger values of Y. Well, okay, this is just the interpretation that we discussed earlier. This is going to be uploaded on Putra Blast. You can read over it. If you don't understand, you can ask me again if you need more explanation. But I think this is the most interesting part of this lecture so far. I like graphs compared to equations. Okay, so do we want to go with this one? Covariance. Okay. Mu of X. Okay, so this is an example on covariance. Let's try to do it. I can't remember what this slide refers to. Never mind. I'll go back to it if I need to. Okay, example, a mobile computer. We have 45 minutes. Let's just stick to 30 minutes of class. A mobile computer is moving in the region A bounded by the x-axis. What? Sounds odd. Why is it moving in region A? Why is it moving? It's a mobile computer. It's moving in the region A bounded by the x-axis, the line x1. So we have the x-axis, this is our x-axis. The line x equals to 1. So if I have 0 over here and 1 over here, I have a line going here. Okay, so I'm just trying to draw it. And the line y equals to x. Line y equals to x is always going to go through the intercept or the origin. And it's going to be like this. So this is y equals to x line. And this is x equals to 1 line. So it's telling us So it's telling us that our mobile computer is moving in the region A, and region A is this triangle. Not that hard, right? If XY denotes the position of the computer at a given time, oh, it's already here, forgot to see Y. This is X. If X and Y denotes the position of the computer at a given time, the joint density of X and Y is given by the following. So this is the joint density, 8XY, if X and Y is within region A. This is what it means, within region A. And if it is not out in region A, meaning to say whatever values outside of region A, the function will be 0. So it only covers inside this triangle that I'm coloring with purple highlighter. Okay, so that's the region. So let's find covariance X and Y. So first, we need to find mu of X and mu of Y. Why? Because the equation tells us that covariance is this guy, mu of xy minus mu x mu y. Let's use this one because this one is hard. Let's use this equation, which is more straightforward. Covariance X and Y is given by mu xy minus mu x mu y. So we need to find mu x, mu y, and also the mu of joint, the joint mu. Joint mu minus mu x times mu y. Okay. Okay, to compute fx x, first of all, to find mu x from a joint density function, you have to find the marginal distribution, marginal density distribution, marginal probability density function. I hope I got that right. So this is joint, but we want only the x component. Remember what we had to do? We had to sum for, if we wanted the marginal for x, we had to sum over all the values of y. If we wanted marginal of y, we had to sum all the values of x. It was the opposite case, right? So same case over here. If we want to find out what is the mu x, we need to know what is the marginal density first. So the marginal density of x, we have already covered. I'm just going to go over. We fix the x and integrate the joint density along the vertical line through x. Okay, bear with me with this one as shown in figure over here. The integration is with respect to y because we are trying to find the marginal density of x. So we have to sum over all the values of y or dy. If we are talking about discrete, over all the values of y. If we were talking about integration or the continuous random variable, we have to sum over dy. Sorry, we have to integrate with respect to dy. Okay, so the integration is with respect to y, and the limits of the integration are y equals to 0 to y equals to x. Why? Why is the limit of our integration this? So let's discuss about this. We have this region. Okay, let me use this region over here. It's much more nicer. We have this region. I want to know what is the marginal density of x. Remember, if we want to find the marginal density of x, we have to sum over all the values of y. It was the opposite case. So if I want to know what is x over all the values of y, I can indicate it with a line. Any line is okay. But in this case, they just put it over here. You can, it doesn't have to be here. This is what I'm trying to say. You can write it over here. You can draw the line over here. It doesn't matter. As long as you indicate, you don't have to draw it for me. It's just for your understanding. As long as you know that it is going over all the values of x. Why does it tell us that it is all the values of x? Because this thing is all the values of x. It is referring to this axis. X is just one value. But for this line, it covers all the values of x. This line covers all the values of x. Sorry, it covers all the values of y, but only one value of x. This is what we want for marginal density function. So the boundary for this is y equals to 0 up to y equals to x. How do I know it's y equals to x? Because this line is actually y equals to x. There's no fixed value. It's y equals to x. It's just a line. It's a function actually. So this is a little bit confusing, I have to admit, but please bear with me. Okay, so we start with our marginal density function. We integrate it from 0 to x. This was the boundary that we have defined, and we put in the function here, and we integrate with respect to y over all the values of y. So this is fairly straightforward. Tricky part is understanding the boundary and also remembering the equation. So for x to the power of 3, your y, you just substitute it. Sorry, it becomes, let me try to do this. 8x y squared over 2. Value goes from 0 to x. So 8 divided by 2 is 4. X y squared. Now I can just plug in the values. What is that? So it becomes 4x cubed because I'm substituting x into my y. So it becomes 4x to the power of 3. 4, 0, 2, 1. For the values of x from 0 to 1. Okay. So that was your marginal density function. We have not solved this question yet. It's a lot of steps. Any questions so far? It's quite heavy, right? No questions? Okay, I'm going to continue. I hope you guys are not sleeping. So to compute the marginal density function for y, same case over here, but we want to integrate over all the values of x. So this line is one value of y and all the values of x. So what is the boundary that I have to integrate? It goes from here to here. What is here to here? Here to here is y, x equals to y. X equals to y because it is on the line, on the function line, and x equals to 1. Just now, it was from 0 to the line. Therefore, it was 0 to x. Here, it is from the line to the 1, to the boundary 1. This line is not y equals to x, it's equal to 1. So your boundary is from x equals to y to x equals to 1. So this is what you plug in. This is the lower value. This is going to be the higher value because it can't go beyond 1. So 8xy, you are going to integrate with respect to x. So same case over here, 8x squared y divided by 2. You would get 4x squared y, and you would plug in y and 1. So this would become 4y cubed. Sorry, it's 4y minus, you start with 1 first. 4y minus 4y cubed. So this is your marginal density function for y. And this is for y from extending from 0 to 1. Not done yet. We just calculated the marginal. We have not calculated the mean yet. So, and then from here, we can now calculate the mean, which is just the regular equation that we used earlier, which is x fx. We can use this equation because now we only have one random variable for our marginal density function, right? If your fx is fxy, then you can't use this equation. If it is a marginal density function, you can because it only has one random variable in question. So now you can use the regular equation that we used earlier, and it becomes fairly straightforward. I think 4x cubed, you integrate with respect to 0 to 1. And this is also from 0 to 1. Okay, so you would get your mean as 4 over 5, and for the y, you would get 8 over 15. And then finally, we can try to solve for our mu xy. We already found out what is mu x, what is mu y. Let me write that somewhere. Mu x is 4 over 5, 8 over 15. 8 over 15. And now we have to find out what is mu xy. So this is going to be a little bit different. For one random variable, we saw earlier that it is x, f, x. For joint mean, it is going to be xy, f, xy. Please keep this in mind because it is not in the definition. Please write that somewhere. It's not in the definition. This is basically expanding the equation. So xy, f, xy, this is your equation for joint probability density function. So now we want to find the mean, and your boundaries are the same as the region, the triangle region, which is 0 to 1 for 0 to 1 for x and 0 to x for y. Why is it 0 to 1 and not x to 1? 0 to 1. Wait, let me double check on that one. 0 to 1 for x and 0 to x for y. Oh, okay. Kejap. Give me a minute. Zero to 1. Okay, I'm not sure about this one. I'm not sure why the boundary is different. I need to double check on this. Double check. Okay. So the boundary for this guy is straightforward. We already discussed how we got this boundary from 0 to x for our y, because if we are integrating over all the values of y, then it is a straight line vertical. Therefore, it goes from 0 to y equals to x, or x equals to y. But for the dx, we have this guy over here. But it's not going from x to 1. Okay, so this is where, okay, I'm not sure about this one. Let me double check on that one. But if we were to apply this equation, xy, 8xy, you would see that you have to solve it one by one. So first you solve with respect to y, okay? So you would get 8y, if I were to expand this first, 8x squared, y squared, and integrate with respect to y, I would get 8x squared y cubed over 3. 8, let me try to write that somewhere nicely. 8x squared y cubed, because I'm integrating with respect to y. I only care about y at this point. I already multiplied x and y into this. So it's 8x squared, y squared, and then integrated, it is 8x squared, y squared. Now it is 0 to x. This is the boundary, so I'm going to plug in 8x squared, x cubed. 0 just becomes 0. So now we have 8x to the 5. Oh, sorry, I missed out the 3. 3 over 3. Okay, so the next one is integrating with respect to x. Oh, okay, so this is why we don't have the x anymore. Because if we were to put in the boundary as x to 1, then it wouldn't be a value. So we can't have that to happen for a mean. But I still need clarity on that one. Okay, so let's just stick to the solution first. So 0 to 1 and 8x6 to the power of 6 divided by 6 times 3 is going to be 8x to the power of 6 over 18, and it goes from 0 to 1. Fairly straightforward. So it becomes 8 of 6. So this is going to be 8 over 18. 6 times 3 is 18, right? 8 over 18. So this is 4 divided by 2 divided by 2, 9. 4 over 9. Okay, so now that we have our mu x, mu y, mu xy, so covariance equation tells us that it is mu xy minus the product of mu x and mu y. So this is what we have over here, and you can find out what is the covariance. The covariance is near 0. It's not a strong positive. If it was a strong positive, I would say it's a value more than 1. So this is close to 0. Therefore, your data would look like close to the mean. Okay, so let's take a 5-minute break because I need to check back in the textbook about the boundary, and then we'll get back to more, or the last one, which is correlation. Give me 5 minutes. Let's come back at 10:38. I know you need the break because it's heavy. Let me look at the textbook. If you have any questions, you can ask me. Otherwise, take your break. Boundary. Marginal. Okay, 2 more minutes and then we're gonna have our last content. I'm gonna clarify on the previous example as well. Just a little bit more, please bear with me. Okay, can I continue even though I said it's 10:38? Let's finish early. Is everyone okay with me continuing? Or you guys are at the bathroom? Okay, I'm assuming that you guys are away. 1 minute to go. Okay, it's time. So I hope everyone is back. Excuse me. Okay, so about the boundary just now. Okay, so here, if we have two boundaries, right? So if I were to flip the boundaries, I would have a dx dy, right? If I were to flip the boundaries, and this would be whatever that is the inner integral, whatever that is the inner integral would be, your boundary would be how we found out the marginal density function, which was a straight line. If it is dx, then I would have a straight line like this. If it is a dy, I would have a straight line like this. So it depends on what your inner integral is. So in this case, your inner integral is dy. Therefore, inner integral is like this. Okay, inner integral, and dx is your outer integral. So your inner integral in this case is dy. So dy is summing over all the values of y's, right? But in this case, we are bounded by the outer integral. We are bounded by the outer integral, which is x. So if we were to sum over all the values of y, but still bounded by x, over all the values of y is this straight line. So we have to follow the same boundary as the marginal density function. But if we are calculating for our outer integral, we are trying to wrap things up. So we use the actual value of the actual value of the function, which goes from 0 to 1. So this is why your outer integral will not have any variable. Your outer integral, I'm going to repeat myself here, your outer integral will not have any variable. So this was what I failed to mention earlier. So if I flip this boundary, if I flip this dx dy, what happens is, I need some space over here. Let me try to write this. If I were to flip this, I know it seems like it's not important now, but if it comes in the exam, you would have to know how to write it, right? The boundary. So xy, 8xy, dy, dx. So this is the same, dx, dy. dx dy. So my inner integral is x, right? I have to sum over all the values of x, but I am limited by y because y is the outer integral. So all the values of x refers to the green line, which goes from 1, 0 to 1. Sorry, is x to 1. X to 1. This one, x to 1. So this is x to 1. But for my outer integral, I would just use from 0 to 1 because the outer integral wraps it up, and how do I say this? You have to have a value at the end. You cannot have a variable as your mean. So the outer integral will not have any variable. Please take note. I also forgot about this. Okay, so I hope that clears any confusion. Please look back at the lecture notes, go over it, and then do some exercises from textbook. Any textbook, as long as it follows the syllabus. I would recommend the ones that I have shown in the Putra Blast course info. The textbook is there. It's not there, you have to Google it. Okay, last one. Last one for today. So correlation. So we talked about covariance, and we said that covariance tells us the relationship between x and y, how strong it is. Is it positive? Is it negative? If it's positive, you would see it more in the first and the third quadrant. If it's a negative, you would see it more in the second and the fourth quadrant. If it's close to 0, which is great, the data will be centered around the mean. And the mean for mu x and mu y is the intersection between the means is our origin. You have to remember that. So for correlation, if x and y are jointly distributed random variables, covariance tells us the strength of the linear relationship between them. Covariance has units. I did not mention this before. Covariance actually has units, which are the units of x multiplied by the units of y. For example, if we are talking about random variable x is the distance in millimeter, for example, and y is the random variable which tells us the area of something, which is millimeter squared. So the covariance will be millimeter cube. It will be a multiplication of the units of this random variable, whatever it is. It can be liter, milliliter, it can be Newton, okay, that's physics. Whatever units that you have to multiply those two together, and the covariance is the product of the units. So if we were to compare between covariance of one type of data versus a second type of data, if they do not have the same units, you cannot compare between them, because obviously you can't compare between apple to orange. If they have different units or different colors, you can't compare them because they are basically different things. So in practice, covariance cannot be used to determine which pairs of data is more strongly related. You know the relationship between x and y for this guy, but if you have a different set of data x and y, sorry, let's say it's z and x, for example, you cannot compare between these two because they have different units. You know the spread of this guy, you know the spread of this guy, but between them, which one is better, you wouldn't know because they have different units. So what is needed is the measure of strength of a linear relationship that is unitless. So this is where correlation comes. So this is our equation for correlation, which is basically covariance over the variance of, sorry, this is standard deviation of x and standard deviation of y. Okay, so covariance, we know how to find that. It was very, very lengthy. I'm pretty sure it's going to come out some way or another. I hope I can simplify it for you. And you have to know how to find standard deviation of x and standard deviation of y. We know this, we know variance. Standard deviation is just a square root of that. And your correlation will always go between -1 to 1 only. Do not give me a number beyond this region, beyond this boundary. If you do have a number beyond this, you know it's wrong. So please do your steps again. So correlation is a scaled version of covariance. Basically what you're doing here is you are getting rid of the units. This is why you are dividing it with the standard deviation. Okay, so this is just applying the equation. Give me 5 more minutes. So this is the function that we saw earlier, the marginal density function that we already calculated. And to apply, to find the correlation, first you need to find out what is your variance or standard deviation. So this one is also, we already saw this equation. It was x squared. Remember that I told you, you have to put in the bracket. Do not put the mean together inside this integration. Remember that equation? So this is the equation. You just reapply it and you find the answer, and this is basically covariance between x and y. And this is your standard deviation because you are square rooting your variance. This is your variance. You can also write it like this. Square root 4889. Okay, it's the same case as this. They are just, putting it together. It's the same case. So this is how you apply it. So I'm going to have this lecture slide on Putra Blast. If this is confusing to you, good, read it because it is confusing. So please revise, do some exercises. There are exercises with solution at the back of this lecture. Go over them. If you don't know how to do it, we can discuss. You can come to my office or you can come to my lab if you need to. Otherwise, our lecture today is done. Okay, any questions so far before I end class? Stop sharing. Everyone's okay? We need to know how to apply the equation. That's it. This is the aim for this lecture because there's a lot. So no questions?
All okay, Doctor?
Okay, so take care, have a great lunch, and I'll see you tomorrow and also in AutoCAD class. Bye. Take care.
Thank you, Doctor.
Thank you, doctor.
Doctor.